Hello and welcome to Two Sigma Presents Machine Learning Models of Financial Data. My name is Rachel Malbin and I work on the engineering education team at Two Sigma. We have a culture of learning at Two Sigma, and my team builds education programs that increase productivity, build connections among our technical teams, and support intellectual development. At Two Sigma, we also have close ties to academia. I have the great pleasure to help bring in professors and grad students to lecture on their latest research and work with employees to develop conference talks. One of my favorite responsibilities is running the Hacker Lab, Two Sigma's internal hackerspace. To learn more about our culture of learning, check out the articles on our blog, Insights. And if you're a student, please be sure to check out our PhD fellowships. I'd like to invite you all to head to slido.com and enter the event code TSPresents, which we will be using for the Q&A at the end of the session. Please submit your questions at any time during the lecture. I'm proud to introduce Justin Sirignano, a member of our Two Sigma Securities team, and also an associate professor in mathematics at the University of Oxford. At Oxford, his research focus is the theory and applications of machine learning, with recent work proving new mathematical results for the asymptotics of neural networks, as well as developing deep learning models for high-frequency financial data. After the talk, stick around to ask questions to Professor Sirignano and other Two Sigma team members. And with no further ado, here is Professor Justin Sirignano.
Rachel, thank you for the introduction. It is a pleasure to speak today at Two Sigma on the topic of machine learning models in finance. Before we begin the presentation, please quickly read this important legal statement. In particular, the information in this presentation is not intended to provide and should not be relied upon for investment advice. Past performance of any models or methods in this presentation does not guarantee future results or performance. Financial companies are interested in using machine learning for prediction and decision-making. An example might be predicting the future price of a financial instrument and then determining, if possible, an optimal trading strategy. Machine learning models have the capability to represent nonlinear, high-dimensional, and sequential relationships in data. These three features, nonlinear relationships, high-dimensional input variables to models, and sequential relationships in time series data, are often present in financial applications. Determining an optimal decision is a more challenging task. Reinforcement learning is a class of methods which can learn decision policies directly from the data. Reinforcement learning trains a model to map the data to an action with the goal of maximizing an appropriate objective function. Machine learning is typically most useful when large amounts of data samples are available. Deep learning models can have hundreds of thousands or millions of parameters. This leads to a model with the power to represent complex, high-dimensional relationships in the data. On the other hand, the large number of degrees of freedom can lead to overfitting if there's insufficient data. High-frequency financial data sets have many billions of data samples, and high-frequency modeling is the financial example that we will focus on in this presentation. To train large models on such large high-frequency data sets, high-performance computing is essential. There are also many applications in finance where only medium-sized data sets are available. In these cases, it may still be possible to apply machine learning using appropriate modeling approaches. However, one must be careful to evaluate whether overfitting is occurring due to an insufficient amount of data. Machine learning is in the process of transforming fields such as computer vision, natural language processing, and speech recognition. Motivated by this success, there has recently been tremendous interest in applying machine learning to finance. Financial machine learning is really a fascinating area at the intersection of computer science, applied mathematics, and economics. The goal of this presentation today is to provide an introduction to machine learning models of financial data, and in particular, present concrete examples of machine learning models of high-frequency data. We will explore two examples of machine learning models of high-frequency data. In the first, we will develop and evaluate recurrent neural networks for modeling price moves. The second example uses reinforcement learning to determine optimal order strategies. Although we will focus on high-frequency data today, there are, of course, many other potential applications of machine learning in finance, including modeling price returns at longer time horizons, pricing financial derivatives, solving high-dimensional partial differential equations, and loan prepayment, default, and delinquency modeling for asset-backed securities. But today we will focus on these examples from high-frequency data. Stocks are mainly traded via electronic markets. In an electronic market, buyers and sellers are matched via a limit order book. I will provide a brief introduction to limit order books before we discuss machine learning models. Investors submit limit orders at prices they are willing to buy or sell at. In the United States equity markets, orders can be submitted in price increments of 1 cent. The example here shows the first few price levels of an order book. Buy limit orders are in blue and sell limit orders are in red. And at each price, the number of limit orders is stated. The lowest price for a sell order is called the best ask price. The highest price for a buy order is the best bid price. If an investor immediately wishes to buy or sell a stock, they can submit a market order. The market order is executed at the best ask or best bid price. Specifically, a market order to buy will be executed at the best ask price, while a market order to sell will be executed at the best bid price. The mid price is the average of the best ask and best bid prices. The spread is the distance between the best ask and best bid prices. In this example, there are no limit orders at $10, and the spread is 2 cents. In the example here, a market order to sell 100 shares of the stock is submitted. This market order is executed at the best bid price of $9.99, and therefore reduces the number of limit orders at the best bid price from 200 to 100. Investors who have existing limit orders in the market have the option to cancel their orders. The example here shows an investor canceling a limit order for 200 shares. The order cancellation increases the spread from 2 cents to 3 cents. That is, the best bid price decreases from $9.99 to $9.98. And there are now no limit orders at the price levels of $9.99 and $10. This example shows an investor submitting a new limit order for 100 shares at $10. This changes the best bid price to $10 and decreases the spread to 1 cent. So in summary, the order book evolves over time as new limit orders are submitted, existing limit orders are canceled, and transactions occur due to the submission of market orders, which are matched with limit orders. Depending on the stock, there can be hundreds of thousands or even millions of order book events per day. This order book data represents the visible supply and demand for a stock. The order flow data is a high-dimensional sequence of the visible supply and demand at a large number of price levels, and we can try to use this data to train machine learning models to predict future price changes. It is important to realize that even if a model can predict future price moves with an accuracy greater than 50%, it still may not be possible to implement a profitable trading strategy with the model. One reason for this is the existence of a non-zero spread, as the example here illustrates. In this hypothetical example, suppose the investor's model predicts the mid price will increase and a market order and the investor then submits a market order to buy 100 shares of the stock. This market order is executed at the best ask price of $10.01. In this hypothetical trade, it turns out that the model prediction was correct and the mid price does increase. And then the investor submits a market order to sell the stock, which is executed at the new best bid price. Even though the mid price increased, the investor lost $10 on this trade, as the profit and loss calculation shows. This is a consequence of the non-zero spread between the best ask and best bid price, which can be viewed as a type of transaction cost. In conclusion, even if a model can predict future price moves with an accuracy greater than 50%, a trading strategy based upon that model may not be profitable and could, in fact, lose money. We will implement a recurrent neural network for predicting price changes in high-frequency financial data. To demonstrate the potential of machine learning to outperform classical statistical models, this deep learning model will be compared against a linear recurrent model. We will use a data set of 3 years of event-by-event high-frequency data for approximately 1,000 stocks. In total, there are hundreds of billions of data samples in this data set. This data set will be downsampled to the times at which price changes occur. The models will be trained on this downsampled data set. A deep learning model will be trained to try and predict whether the next price change is positive or negative, conditional on the order book data. This is a binary classification problem. The price will either go up or down at the time tau k plus 1. Due to the large size of the data set, model training is parallelized across a large number of GPUs. A crucial question is whether a nonlinear machine learning model, such as a recurrent network, will outperform a linear statistical model. This would only be the case if the recurrent network is able to learn nonlinear relationships in the data. We will use a type of vector autoregression model as a benchmark. XT is the order book data at time t, and the vector MT is a linear representation of the previous order book data in the sequence. This actually can be considered a linear recurrent network. Recurrent neural networks are very similar, except the vector MT will be a nonlinear representation of the previous data in the sequence. In deep learning, we often call this variable MT the memory state. In a recurrent network, the update for the memory, MT, uses a neural network G of M x theta, which has as inputs the current memory state and the current order book data. The parameters for the recurrent network are theta, and they must be estimated or learned from the data. The prediction at time t is y hat t. At each time step t, new data xt arrives. The memory state is then updated, and a prediction is made. We would like to select the parameters theta to minimize the objective function in equation 7. That is to predict the target data yt as accurately as possible. In principle, the backpropagation algorithm can be used to optimize over this objective function. For each optimization iteration, the recurrent network will be run forward through the entire sequence to generate the predictions. Then, in the backward step, the gradient will be calculated by the chain rule. The computational cost for a single optimization iteration is therefore proportional to the length of the sequence, capital T. This is extremely computationally costly for long sequences. In practice, it is common, therefore, to use the truncated backpropagation through time algorithm to reduce computational cost. This is an online optimization algorithm where the recurrent network is continuously marched forward through the sequence. Every tau steps, we will update the parameters. Backpropagation will be calculated tau time steps backwards, and then the chain rule will be truncated. Tau is chosen to be much smaller than the length of the sequence, capital T. Due to this truncation of the chain rule, the computational cost of each parameter update is only order of tau as compared to order of T for the backpropagation algorithm. Therefore, it substantially reduces the computational cost. Of course, the trade-off is that the truncated algorithm is not using the correct direction of steepest descent in the parameter updates. It is a computationally tractable approximation, which has error. Another way to view this, the truncated backpropagation algorithm is that information from previous times in the sequence is flowing forward via the memory state, but we are not fully optimizing over the entire sequence when training the model. We've described the truncated backpropagation algorithm in words. Let us now precisely state the algorithm in terms of mathematical equations. At the kth optimization iteration, we will construct the objective function in equation 8 for a subsequence of length tau. We will optimize only over this subsequence, which we denote as a function of theta of k in equation 9, and we will truncate the backpropagation algorithm at the time t equals k times tau, where the memory state is treated as a function of theta of k minus 1. The parameters are then updated according to equation 11, where the learning rate is alpha of k. Optimization of recurrent networks is similar in spirit to optimizing a multi-layer feed-forward network with capital T layers, where capital T is the length of the sequence. A well-known challenge is the vanishing gradient problem, where the gradient with respect to the lower layers in the network will be small in magnitude. This leads to stochastic gradient descent converging very slowly. A similar phenomenon can occur in recurrent networks, where the magnitude of the gradient with respect to the memory states far in the past may be small, and this can make training slow. Here's an example of training multi-layer networks on the classic MNIST image dataset. The top plot shows the accuracy versus the training time. All of the networks converged in accuracy well above 90%. However, the networks with more layers take substantially longer to train. The bottom plot shows the gradient magnitudes for one of the lower layers in the networks. The networks with more layers, that is greater depth, have much smaller gradient magnitudes. This leads to much slower training for stochastic gradient descent methods. In the context of recurrent networks, it can also make it challenging to train recurrent networks to remember data from far in the past in a sequence. One of the most popular types of recurrent networks is the LSTM network. It is a relatively complex architecture, but its key components are element-wise functions called gates, which are designed to efficiently update the memory state with the goal of helping the model remember data from far in the past in the sequence. The forget gate can set elements of the memory state to 0. The input gate can add information to elements of the memory state. The motivation behind this architecture is that in principle, the forget gate can remove information which is no longer useful, and the update gate can replace it with new information. This is a diagram of the LSTM architecture. The previous memory state and the current data xt, which are highlighted in red, arrive and then are updated by the LSTM internal operations, such as the input and forget gates, which are highlighted in blue. The updated memory state is then sent to the LSTM unit at the next time step. We will train a series of models on the high-frequency order book data set and then evaluate their performance on a test data set. For each stock, we will calculate the accuracy of the model for predicting the direction, up or down, of the next price change. Specifically, the accuracy for the stock I will be the number of times the model correctly predicts the price change over the total number of price changes times 100%. Models will be compared in the following way. For the ith stock, we will compute the difference in accuracy Li between model 1 and model 2. If model 1 is better than model 2, Li will be positive. We will then report the distribution in a histogram of the difference in accuracy Li across a large number of stocks. Let us begin by comparing the linear model against the LSTM recurrent network. The left plot is a histogram which shows the increase in accuracy of the LSTM versus the linear model across approximately 500 stocks for NASDAQ limit order book data. The recurrent networks consistently outperform the linear model. The right plot displays the absolute accuracy of the models. The linear model is in blue and the recurrent network is in red. The test data set that is used here is roughly 500 stocks over a 3-month out of sample test period. And for this test data set, we see that the deep learning model clearly outperforms the linear model. It is able to learn nonlinear relationships in the data, which lead to a more accurate prediction. The deep recurrent network maps the order book data sequence, referred to here as the order flow, to a conditional probability distribution for the direction of the next price move. An important question is whether this recurrent network function F is universal across a large number of stocks, or if each individual stock should have its own function F. If the relationship between the order book and price moves is similar across the universe of stocks, then a single deep learning model can be trained for all stocks. I will refer to this as a universal model. On the other hand, if the relationship between the order book and the price moves varies across different stocks, then each individual stock should perhaps have its own model. For example, perhaps the price dynamics of IBM are very different than General Electric, in which case each would have its own individual deep learning model. An equally important question is how stable is the model across time? In particular, will it still be accurate many months out of sample after the end of the time period it was trained on? From a scientific perspective, we would like the relationship between the order book data and the price moves to be universal across stocks and also stable across time. In addition, there are also important practical implications of this. If the relationship between the order book data and price moves has some universality across stocks and is relatively stable across time, a deep learning model can be trained on the combined data sets of hundreds or thousands of stocks over long time periods. Using more data will lead to a lower likelihood of overfitting. And this is important for deep learning models, which have large numbers of parameters. More data will also potentially allow us to train larger models, which could achieve higher accuracy. This can also be considered a form of transfer learning, where we try to use data from, for example, IBM to improve a model for General Electric and vice versa. Finally, from a computational standpoint, training a single universal model should be less costly than training thousands of stock-specific models. In the examples that I will show in a moment, there is strong evidence for a universal price formation model mapping the order flow to price changes. This model is stable across long periods of time, even a year out of sample. And this allows us to build a single universal model for large numbers of stocks and over long periods of time. In this experiment, we train a universal model that is a single recurrent network model trained on the pooled data of hundreds of stocks and compare it against stock-specific models. The stock-specific recurrent networks are trained individually for each stock. If the order book dynamics are not universal, we would expect that the stock-specific model would outperform the universal model. The histogram plots the increase in accuracy of the universal model versus the stock-specific recurrent network models across approximately 500 stocks in a 3-month out-of-sample time period. The universal model consistently outperforms the stock-specific models, as the histogram shows. This suggests that different stocks share some universality to their order book dynamics, and this can be used to reduce overfitting in the training of machine learning models, potentially leading to improved model accuracy. This universal recurrent network model is also able to generalize to new stocks, at least in the experiments where we studied it. Using a pool of 1,000 stocks, we train a model on approximately the first 500 stocks and test on approximately the remaining 500 stocks. The test data set now consists of stocks the model has never been trained on. The training time period is January 2014 to May 2015. The test time period is June to August 2015. The left plot displays the histogram of the absolute accuracy of the model for this out-of-sample time period. The accuracy is consistently well above 50%. The right plot is a histogram of the accuracy for the time period January to March 2017, which is over 1 year after the end of the training data set. This demonstrates model stability for more than 1 year out of sample. As mentioned at the beginning of the presentation, high-performance computing is essential for training large models on large high-frequency data sets. The training of the universal model shown in this presentation was distributed across 25 GPUs using asynchronous stochastic gradient descent. At each training epoch, random subsets of the data set are loaded into the memories of the machines. Data is moved to the GPUs, where the gradient is calculated. Each machine then asynchronously sends the gradient to the parameter server to update the model, and the updated model is sent back to the machine. The model updates occur asynchronously, meaning machine I does not wait for machine J to finish calculating the gradient. In the second example in this presentation, we will use reinforcement learning to develop order submission strategies. Optimal execution tries to address the following question. Given a decision to submit a buy or sell order for V shares, how should the order be submitted to achieve the best price? For instance, for a buy order, one would like to minimize the average execution price in equation 13. Deciding how to submit the overall order is a challenging problem. The overall order can be broken up into smaller submitted orders, and one can choose whether to submit limit orders or market orders. The times and sizes of the orders can also be chosen. As many in the audience probably know, the optimal policy for a Markov decision process satisfies the Bellman equation. If the transition probability function to compute the conditional expectation of the state process xt plus 1 is known, the Bellman equation can be in principle solved. Once it is solved, its solution v of xa yields the optimal action for each possible state. However, in practice, the transition probability is typically unknown. Furthermore, if xt is very high dimensional, it will be computationally intractable to solve the Bellman equation with traditional numerical methods. Reinforcement learning addresses these challenges, and it tries to learn the optimal policy from observations of the state process xt, its transitions from xt to xt plus 1, and the reward r of xt at, where at is the action selected at time t. Let's now use reinforcement learning to learn order strategies for a very simple order execution example. To train the reinforcement learning model, we must be able to accurately simulate the executed price for an order strategy. For a small order of 1 share, we can accurately simulate the executed price directly from historical order book data with some minimal assumptions. For limit orders, this requires event-by-event tracking of the order to determine when in the historical data sequence it would have been executed. We will train and evaluate reinforcement learning algorithms for 2 cases. The first case will be optimal execution of a market order of size 1, that is for 1 share. And the second case will be optimal execution of a limit order for 1 share. These are, of course, idealized examples, as in practice, financial institutions are interested in optimal execution of much larger orders. However, it is a first step towards developing a reinforcement learning algorithm for more challenging cases. We will first consider market order only strategies. Given an order arrives at time t to buy 1 share of a stock, how should we select the time tau to submit a market order to execute the trade? We would like to buy the stock for the best possible price. That is, we would like to maximize equation 15, where our strategy for selecting tau can be a function of the order book. In reinforcement learning terminology, equation 15 is referred to as the expected reward. If the best ask price, AT, is a martingale, for example, it has no predictability, then immediately executing the market order at the initial time, lowercase t, is optimal. In this case, the value of the objective function in equation 15 is 0. And this serves as a benchmark for our reinforcement learning strategies. The question is, can we learn a strategy which provides positive cost savings for the order execution? At each discrete time, up until the time horizon capital T, the reinforcement learning model chooses whether to submit the market order or wait. If it chooses the action to wait, the model is predicting that the best ask price will decrease, and it can buy the stock at a lower price at a later time. The reinforcement learning model will select the time to submit the market order. Using this model, we will sample actions and simulate outcomes. Specifically, we will simulate what price in the historical order book data the order would have been executed at. Using the simulated outcome, we can then optimize the reinforcement learning model. The advantages of reinforcement learning, as I mentioned before, are that we can try to learn a decision model when the state space is very high dimensional and when the state dynamics are unknown, which are both true for order books. In the following examples, we will use a limit order book data set from the NASDAQ stock exchange and downsample it to 1 second time intervals. The downsample data set will be used to train and evaluate models, with the model making a decision every 1 second. The input to the reinforcement learning model is the limit order book data, the limit order book at each time. The model is trained on 1 year of data, and its performance is then evaluated on 6 months of test data. It is very computationally costly to train the reinforcement learning models at longer time horizons. In particular, simulation of the limit order strategy, which I will show later, requires sequential marching through each event in the order book data set, which requires substantial computational time. We will simulate results across a universe of 100 stocks with time horizons of 10 and 60 seconds. If the order has not been executed by the final time of capital T seconds, in this case 10 or 60 seconds, we will immediately submit a market order at that final time. The results for a market order only reinforcement learning strategy are displayed here. The x-axis is the name of the stock. The y-axis is the cost savings. That is the average improvement in the executed price as compared to immediately submitting a market order at the initial time. As mentioned earlier, if we immediately submit the market order at the initial time, the cost savings would be 0. The cost savings on the y-axis are reported in basis points. 100 basis points is 1 cent. Results for 2 different time horizons, 10 seconds in purple and 60 seconds in turquoise, are displayed. We observe that the reinforcement learning model consistently provides a cost savings, a positive cost savings across these 50 stocks, although with significant variability. Some stocks have a small cost savings while others have a larger cost savings. Results for another 50 stocks are displayed here. Notice that in general, the cost savings increase given a longer time horizon, which is shown in turquoise, the 60-second time horizon, and the 10-second time horizon is shown in purple in the plot. Let's now consider a simple limit order strategy. Given an order arrives at time T to buy 1 share of a stock, we immediately submit a limit order at the best bid price, BT. Let gamma T be the time at which this limit order would be executed. We have the option to cancel the limit order at discrete 1-second intervals within the time interval lowercase t to lowercase t plus capital T. Capital T here is the time horizon for the strategy. If we cancel the limit order at time tau, we will immediately submit a market order to the best ask price to execute the trade. If the limit order has not been executed by the final time, the limit order is canceled and a market order is immediately submitted. The expected cost savings from this strategy is given in equation 17. The expected cost savings from a strategy to select the cancellation time tau is given by equation 17. We would like to use reinforcement learning to train a model to adaptively select the time tau to maximize equation 17. To train the model, we need to be able to simulate whether or not the submitted limit order for 1 share will be executed in the time interval of length capital T. Under some minimal assumptions, we can use the historical order book data to do this. At the initial time a limit order is placed in the order book, as shown in red, we then track event by event to determine when the limit order would have been executed, for example, in blue. It is possible that the limit order is never executed during the entire day. Using this simulation, we can train and evaluate reinforcement learning models for selecting the cancellation time in the limit order strategy. The cost savings from this simulation for time horizons of 10 seconds and 60 seconds are displayed here. 10 seconds is in purple and 60 seconds is in turquoise. Similar to before, the x-axis reports the names of the stocks and the y-axis is the cost savings. Results for another 50 stocks are shown here. The reinforcement learning strategy consistently provides a positive cost savings, although again, the cost savings varies, being small for some stocks while relatively large for others. The reinforcement learning limit order, and market order strategies are compared on these plots. In purple, we have the limit order reinforcement learning strategy. And in turquoise, we have the market order only reinforcement learning strategy. The limit order strategy slightly outperforms the market order strategy, although for some stocks, the outperformance is more significant. In summary, several examples of deep learning and reinforcement learning models for high frequency data were presented today. There are many open challenges that remain to be addressed, including developing better optimization methods and developing deep learning architectures specifically designed for financial data, merging reinforcement learning with accurate simulations, for example, for larger order sizes, and also leveraging larger scale data sets of data from a variety of sources and time frequencies. Finally, there are many students in the audience today, so I will conclude with some suggestions for how to learn more about the machine learning field. It is really important to practice implementing models on large-scale data sets. The best way to learn machine learning is really to implement all of the well-known models for the classic data sets. Understanding the mathematical theory of machine learning is also important, as this can provide guidance on how you train and implement the models. Experience in deep learning libraries such as PyTorch or TensorFlow is essential. Experience in high-performance computing for parallelizing the training of models is also valuable. In order to try and apply machine learning to financial data, it is also certainly very helpful to have taken some courses in quantitative finance. That concludes my presentation. I would like to thank everyone for joining today, and I look forward to hearing some questions from the audience.
Thank you so much, Justin. That was fascinating. So it is time now for our Q&A. And to answer our most popular question up front, yes, this session has been recorded and will be up on our YouTube channel. Please submit all your questions using slido.com and use the event name TS Presents, all one word. We're now going to be joined by Justin's teammate, Ilya Vinogradov, and Kyle Irwin and Katerina Resio-Farias from our recruiting team will be joining Justin and Ilya.
Thank you very much, Rachel. Thank you, Justin, for the very interesting talk. So we're going to take questions. So yeah, please feel free to ask about 2 Sigma or about the talk or about anything else indeed. So the first question I'd like to ask is about world events. The financial market is highly affected by world events. So during different years, the models that best apply might be very different. Justin, can you maybe address this in some way?
So it is true that financial markets can change over time. In the example I showed, the model was stable for a year out of sample. It's a good question whether for longer time periods it will remain stable.
Thank you. A question maybe for recruiting. Can you speak a little bit about our hiring geography? Where do we hire from? What countries are we based in, and so on?
Yeah, so I saw in the slide someone was asking about India specifically, but like Ilya is referring, we do hire from different places around the world. We have offices not just in the US. So really if you're looking for quant trading, which I think was what the question was asking, we focus most of our hires in the US, specifically in our New York office, because that's nature of the work is IP sensitive. But we do also have some quant traders in our London office, just a smaller subset there. But yes, we are recruiting for multiple areas. And yeah, like I said, offices all over. So feel free to visit our website and specifically the careers section to see if there are any areas that are of interest to you.
And to piggyback off of what Katerina mentioned, so and I represent, so I recruit for the AI research organization at 2 Sigma as well as engineering, and so we do have offices all over the world, and we do hire from individuals in different countries all over the world. Now, we don't have a full-time remote policy, work from home policy, so there would be some expectation if you were to work at 2 Sigma to operate out of the office, in which you applied into, but that is something that, of course, that we work with through with each individual. And currently, just in case anybody's wondering, our current hybrid, policy, work from the office policy is 5 days, in the office per month. So effectively 1 day per week. And that's, again, something that we try to remain, keep very flexible with individuals. But again, with that, as long as if you are applying into 2 Sigma, as long as you're open to relocation, if you don't reside in one of the areas in which we have an office, it is something that, again, that would be the general expectation there.
Yeah, and one quick follow-up to that. We do have a team called Alpha Studio that partners with researchers and other roles all over the world. So for that, you don't actually have to be in one of the office locations. So if you're interested in doing online research or other kind of work that's remote, feel free to check out our Alpha Research website as well.
Yeah, and a lot of that's part-time as well. If there are students on here too that just want to do some type of part-time research or work or dabble in the financial domain at all, that's a great opportunity. It's a good point, Katerina.
Thank you, Kyle and Katerina. Another question for Justin. So what book or course on quantitative finance would you recommend?
I think it's good to take a few courses in quantitative finance, especially if you're interested in machine learning. There's recently been more and more courses at universities on machine learning models in mathematical finance. So that would certainly be a good course to take. Certainly all of statistical modeling of financial data type courses are also very good to take. Understanding probability is also very useful because even a lot of quantitative finance is based upon applied probability. So having a good probability course as well as a applied probability course that deals with mathematical or quantitative finance is very helpful. And even in machine learning is really uses probability, uses statistics, uses optimization, uses computer science. So having courses in each of these areas is very helpful to machine learning, whether or not it's in finance, but including in finance as well.
Thank you. Another question probably for Justin, but maybe I can chip at it also. So what languages was the code written in for the project that you mentioned? What libraries did you use?
So the examples in this presentation were in TensorFlow and PyTorch. And these are the 2 well-known deep learning libraries. They can be used actually for much more than deep learning. They can be used for machine learning or even applications outside of machine learning. So they're very useful libraries to know. I personally recommend PyTorch of the 2, but they're both very widely used and many people use both.
Thank you. I can just add that we use whatever languages work best for the given task, and there are many tasks. So there isn't one language that fits every need. A couple of quick questions for recruiting. Does 2 Sigma hire interns off cycle, like fall or winter?
Yeah, happy to take that one. So we have in the past, certainly. Right now, the focus for us is to hire interns over the summer, just so that they can have really full summer, usually 10 weeks long internship, where they can focus on a project from start to end. And, most of the folks that we hire for that would be in their penultimate year of study, so that then we can ideally give them a return offer to join full-time after they graduate. That said, we do hire at different times of the year as well. For example, we currently had 2 data science interns in the spring, and we have had also quant researchers in the fall as well. So I think, like I said, the main focus is for the summer, but we do make exceptions for different times of the year as well. And we might, going forward, implement that full-time as well.
A quick follow-up with regard to the calendar. So what's your advice for people graduating in December in terms of applying for full-time roles, for example?
So you're saying, so for people graduating in December, you can start whenever full-time. It's not that you have to start specifically in the fall or in the summer or in the spring. Obviously we want you to start as soon as possible if we give you an offer. So if you start in December, ideally you would be starting a few months after that. Of course, if you want to take time off in between, that's totally understandable. But yeah, you can start as a full-timer any time of the year.
Yeah, exactly. We do hire on a rolling basis there. I think you see the majority of hires, especially if you're looking at undergrad as well as master's programs, those fit those typical December or May cycles. So there's a larger cohort of individuals starting at that time. However, especially for PhD grads or individuals that want to start off cycle, that is something we're amenable to for sure. I think the main goal for 2 Sigma is to really hire the right people, right? So it's irrelevant, not as relevant to start you in at a specific time.
Great, and there is another question for recruiting that just come up. I think it's very interesting. So what is an example of a project that a student can complete on their own time that would aid in developing relevant skills and would also be interesting to a recruiter?
The last part you said, it would also be interesting to a recruiter?
Yeah.
Okay. I can speak on the quantitative research side of things in data science, because that's where I recruit for. Unfortunately, can't share a specific example just because the nature of the work is IP sensitive. But more broadly, I can share that basically the project will consist on finding patterns and trends in data, utilizing the scientific method to test a hypothesis, and creating tools or research that your team will continue to use even after you go back to school. It's not going to be anything simulated. You'll be very much working with real data, real research. So the idea is that if you do well on it, your team will continue to build up on it even after after the internship is over. So it's a great experience to get yourself involved in what the real work looks like at 2 Sigma.
Yeah, to add on to that, especially more pertinent to this talk, I think in more the AI, deep learning, ML space, anything really applicable, any type of kind of deep learning, machine learning approaches that can be applied, especially in the real world. I think one thing that's really important for 2 Sigma is real world problem solving, because that's a big emphasis of ours. So anything you can highlight there, especially ownership of that, right? If it is something that you're working with individuals within academia and different projects on, really highlighting as well what you owned in a part of that is something that I think resonates with myself at least, right, as I'm reviewing resumes.
Thank you. That's I don't even think I can add anything to this. It's very thorough. One question is about fundamental investing roles at 2 Sigma versus quantitative. Where do we stand in terms of non-quantitative work?
Yeah, so we do have a fundamental equity research team that works closely with our quant research, with our engineers, data scientists, and other areas in the business. And they are actually hiring right now, so as well as the quant research roles. So if you're interested, definitely encourage you to go to our recruiter's website.
So a question for Justin, maybe it's similar to what was already asked. So would a similar reinforcement learning setting be useful in optimizing automatic trading executions where traditional trading strategies fail, such as momentum crashes? So how do you suggest modeling the expected forward reward in such a case?
I mean, that sounds like an interesting application. I haven't really considered that. So I don't have a good answer at this time, but I think it's a good question.
Thank you. Another question for recruiting. I'm also very curious. So what exactly is the difference between a data scientist and a quant researcher at 2 Sigma?
It's very similar. They're both in our modeling and trading space. I would say that, obviously data science is more specifically focused on the data science aspect and feature engineering and feature modeling, whereas quantitative research sees more of the complete picture of trading from start to finish. Not sure if that was helpful, but yeah, basically data science is more specified, whereas quant research has a whole picture.
Thank you. And maybe we'll just take 1 or 2 final questions. So please upvote if you're interested, or submit. What is the office culture like when organizing a meeting with others? Are we expected to have a presentation prepared, or is it more casual? So I think I can answer that since I work at the company, and I do research, and I don't do many presentations, to be honest. Maybe I've done 1 or 2 in several years. So there are occasional meetings where you showcase your work, like Justin is doing right now. And in that case, yes, you really want a very clean and clear presentation like Justin created. But more commonly, we interact casually. Just want to talk to someone, go to meeting room. There is a whiteboard, maybe more than one, and yeah, then you can talk about whatever you want. Okay, so I see some questions upvoted. Okay. Okay. So I think this is for Justin. How could you explain a generalist model? How can a generalist model outperform a specialized model?
So I think this question is in reference to what I referred to as a single universal model versus the stock specific models. And so the stock specific model has much less data to train on, so it may overfit. So that's one reason. It may overfit because it has much less data, whereas a single model trained on the pooled or combined data of many stocks has much more data. So you can potentially build a much larger model, more parameters, more degrees of freedom, without with a lower likelihood of overfitting. So that's one reason. And a closely related reason is the idea of transfer learning, which I mentioned in the talk as well, where perhaps you have one stock that has a period of, say, this is just a hypothetical example, a period of high volatility. Okay, and then you have another stock that's never had high volatility in the historical data sequence you've studied so far. Okay, if you train stock specific models in isolation on these 2 different stocks, when the regime changes, meaning when the high volatility stock becomes a low volatility one and the low volatility stock becomes a high volatility one, okay, it will have never seen that type of data before, and the stock specific models may have some trouble. Now, the universal model, the hope is at least, is by training on the combined data of many stocks, right? Even if one particular stock, in terms of its historical data sequence, has not seen every possible regime, maybe you've seen it elsewhere in other stocks, and hopefully the model can learn essentially to generalize or use to sort of transfer the learning from the other stocks to the stock that's never seen that regime before.
Thank you. thanks all. I think our time is up for questions, and I have to pass it back to Rachel. But thank you very much for listening.
Thank you all so much for being here. Thank you, Justin, so much. Thank you, Ilya, Kyle, and Katerina for taking the time to do the Q&A. That is all the time we have, so thank you for joining us. To learn more about Two Sigma, check out our blog at twosigma.com/insights, and you can check out openings at twosigma.com/careers. If you have any questions regarding applications, please contact recruiting@twosigma.com. And to be notified when the video is posted, you can follow our blog at twosigma.com/insights, or you can follow our LinkedIn, and we'll also put an announcement up there. Thank you so much for being here today, and have a wonderful evening.